So let's go ahead and graph a couple of exponential functions. So my first example here, f of x equals 2 to the x. The first thing I want you to notice is where the variable is. It's up here in the exponent position. So that's the number that we're going to replace. That's the number that changes each time. This 2, that is the base, and it is constant for this entire example. So since this is probably our first time graphing exponential functions, we're going to go ahead and use a t-table to get our points to plot. So the first x value I chose, I picked integers just because they're easier. So if x is negative 2, I have to come up with the y value. So f of negative 2 means I have, I'll just do a little workspace down here, my base 2 raised to a negative 2. And we all remember if we have a negative sign in the exponent, it's the reciprocal of the base, so 1 over the base 2. Now this 2 gave up its negative sign to do the reciprocal, so I have 1 over 2 squared, 1/4. So a similar process to find 2 to the negative 1. So x is negative 1, 2 to the negative 1, right? Replace both x's with the same number. 2 to the negative 1 is 1 over 2 to the positive 1. 2 to the 0, anytime 0 is in the exponent, it spits out a 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. So each time I'm just replacing the x, the exponent of 2, with a different integer. And you'll notice that all of my y values are powers of 2. Okay, so let's go ahead and plot those. So if x is negative 2, y is 1/4. So that'll be tough to see. We'll put it there. If x is negative 1, y is 1/2. Okay, it should be a little lower, but that's okay. If x is 0, y is 1. So you all know the special name for that point. If x is 1, y is 2. If x is 2, y is 4. If x is 3, y is 8. If x is 4, it's 16. I'm off my, oh, I can maybe squeeze it there. 1, 2, 3, 4. So if I connect these points, maybe make my dots a little bigger so they get on my line. Okay. This is the graph of an exponential function. It continues on forever up and to the right. Right? I just would have to be patient, right? Going to all of those x values to the right. What about over here on the left? Do you suppose we could have evaluated when x was negative 3? Absolutely. It just gets smaller, smaller and smaller. Those of you with graphing calculators, you're going to want to be careful because your resolution is going to drag this tail right into the x-axis, and it doesn't go there. It's going to just get closer and closer the further to the left you go, but it won't actually touch it. So that has a special name. That's an asymptote. So my graph is asymptotic to the negative x-axis. So what's the domain of this function? What x's are we allowed to plug in? Well, I plugged in negative ones. I plugged in a 0. I plugged in some positive integers. Well, I've connected my dots too, so it's kind of a giveaway that all of the numbers in between are there as well. But let's just make sure. So let's just do one fraction. And if it works for one fraction, we'll assume it works for all. So let's say x is 1/2. So f of 1/2, so that's 2 to the 1/2. And fractional exponents, remember those are radicals. So base is my radicand. That 1/2 exponent, the numerator is the power of the base, the denominator is the index, so it's the square root of 2. So if x is 1/2, remind where everybody is, so here's where x is 1/2, and the y value is the square root of 2, like 1.4-ish. Okay, so I can use positives, negatives, 0, and fractions. That domain is all real numbers. Or if you're using interval notation, remember negative infinity to positive infinity. Now about the range, what kind of y values are we getting out? Well, I've got lots of positive ones. I've got, I can't get negative, so there's nothing I can take the number 2 and raise it to turn it negative. And there's nothing I can raise it to get it to be 0. So it is always bigger than 0 and not including. And remember, the interval notation way to say not including is the parenthesis. You might also use just y is greater than 0 for your range. So this is just a general exponential function graph. So like you might have done before, we can take this general graph and we can shift it. So we're going to take that basic shape and we're going to practice shifting it. So my first one, g of x equals 2 to the x plus 3. So I'm going to take that basic shape we had before. This plus 3 happens after we raise 2 to the x power. We're going to add 3 to all of those y values. So you'll remember from before that takes our original graph and moves it up 3. So all of those points we had before move up 3. Let's see, when x was 1, I was at 2, so now up 3 from that. 1, 2, 3. That was at 4 to start with, and now up 3. 1, 2, 3. Here's where it gets a little tricky over here where I had that asymptote. So the asymptote is actually what I'm going to lift up 3 to get my lower boundary. So it used to be right here where y is 0, right? My x-axis is y is 0, so move that up 3. 1, 2, 3. And that's where I'm going to do my dotted line for my asymptote. I just want to get kind of an idea of what my picture looks like. I'm not doing exact graphs here, I'm just getting an idea. Another way you can think about it, so you can reason your way through, right? This 2 to the x part, right, of getting my y's, this 2 to the x part can never be 0. It always has to be a positive amount. So I have 3 plus a positive amount. Even if it's really, really small, it's always adding something to 3. So y equals 3 is my bottom line, right, that asymptote that I've drawn across. And then everything else adds to it. My domain for this one stays all real numbers. Right? I can still plug anything I want in for x. But my range now, my range starts at, right, it starts at 3 now, and it goes from 3 on up. I can't get any of the numbers between 0 and 3 anymore. All right, let's do one more. This one's a little trickier to see because there's really only a couple of points we can plot on there without being tedious. So this is 2 to the x, and now I have plus 2 up top here with the x. So that's taking my other graph, my 2 to the x graph, and moving it, remember when it's plus inside, left 2. So I might take that y-intercept and move it left 2. I'm not moving my graph up and down at all, so my asymptote will stay here on the x-axis. And just to make sure, let's go ahead and find our new y-intercept. That'll be our second point. So how do we find a y-intercept? Yep, 0 in for x. So 0 in for the x means I have 2 to the 0 plus 2. 2 squared, 4. There's my y-intercept. And there's my graph. It's the original graph we had up top, but now it's shifted to the left 2 spaces. Okay, so just to generalize, for any other base, so I did base 2, but they could be a base of any number. Aha, hold on. I'm going to, has to be greater than 0. Because think about it, if it was negative, it would, right, change back and forth with even and odd integers. And then if it was a negative number and I had a 1/2 as x, then I'd be taking the square root of a negative number, and we can't do that either. Okay, so any other base that's bigger than 1 its graph looks just like our 2 to the x graph. Now, it might be steeper or flatter or, well, I guess those are the options, steeper or flatter, but it has the same basic shape, the same domain, the same range, and the same y-intercept at 0, 1. The other thing that might happen is my a, my base, can be a fraction. It can be any number between 0 and 1 as well. And what that graph looks like is the graph we just had, except it is reflected over the y-axis. So if you're feeling particularly smarty pants right now, you can do a little rationalizing and show, with your knowledge of negative exponents and your knowledge of shifts and reflections, that this makes sense. Try it with a equals 1/2 and do a little exponent manipulation and you can see it. So one more thing before we go, and that's this very special base called e. And e, if you have any sort of scientific calculator, you're going to have a button on there that has an e. It might be a second feature on a button that you see that says ln. And e is just a number. It's kind of like pi, but it's different. It's a different value, but it has the characteristic that it keeps on repeating forever and ever and never repeats or terminates. And its number is about 2.7. So since 2.7, right, is bigger than 1, the graph of y equals e to the x, and you just say it out like that, looks just like our graph of 2 to the x. And it has the same y-intercept and the same domain and the same range. It's important to be comfortable with e to the x because the next thing you'll probably talk about is that second feature, that ln button, which is the natural log.